Welcome to the first video in Unit 6, which is actually Chapter 7. This is kind of a fun chapter. It takes us away from trigonometry for a little while, and it studies something called conics. So what I would like you to do is, if you need to pause the video and copy all this down, and then as I talk through it, you can also do that. Conics is where a plane intersects a double-naped cone. And as you can see, so it's like having a cone stacked on top of one another at the point. And if you take a plane and you slice that cone, and if you slice it in this form, you're going to get a shape on that cone that's going to be what we call a parabola. If you take this plane and slice it directly parallel to the cone, you get a perfect circle. If you do it at an angle this way, you're going to get across both sides. You see how this went to the top and to the side? This goes across both sides of the cone at an angle. That's what we call an ellipse. You can also have a plane that slices both cones, which gives us essentially what look like two parabolas. We call that a hyperbola. So the set of all points that fulfill this geometric property we call a locus of points. And so you're going to see this equation in this form. And to be honest, we don't very often have the b term, an x and a y term. We normally have an x squared, possibly a y squared, an x and a y, and then an integer, that f at the end. We don't normally have a b term or an xy term. You can, but you don't always. Now, just to cover all our bases, you can also have something called a degenerate conic, and kind of a weird name, but that's if your plane slices this shape, this double-naped cone, such that it goes exactly where they are meeting in the middle. Well, that's going to give you a point, and that's called a degenerate ellipse. Or you can have the line go exactly along the side of the two cones, and it makes a line. And we call that the degenerate parabola. Here, if it intersects, if you have two lines and they intersect both sides of the cones, then we call that the degenerate hyperbola. So I wanted you to also be aware of that vocabulary. Speaking of vocabulary, there's quite a bit in the conics unit. So what I would like you to do is, I'm going to quickly talk through these, but you may want to pause the video and copy this down first. When you have this vocabulary, I'm going to scoot this up a little bit, zoom in here for you, and you have the first lesson that really only focuses on parabolas. So we kind of talk about all the conics, and then we're going to really focus on parabolas in Lesson 1, ellipses and circles in Lesson 2, and then hyperbolas in Lesson 3. The parabola is a set of all points in a plane that are equal distant from a fixed line that we call the directrix, and the point, the focus. Now, this is important to note that these are not on the parabola, but they are points and lines that help us determine and achieve the parabola equation. The focus is a point that is always, always, always inside the parabola. Very important. The vertex, which you've already familiar with, but that is a point that is halfway between these two, the directrix, that line, and this focus. So sometimes we'll be given these 2 points and this line, this point and this line, and you have to find the point in the middle, which would be the vertex, where that parabola is changing direction. The axis of symmetry is the line that splits that parabola right in half, and it reflects over that line. The distance P is the distance from the vertex to the focus. And then if you go outside the parabola from the vertex to that directrix, it's that distance is a distance of P. So sometimes you're given that distance so that you can achieve the focus and directrix. Sometimes you're given the information and you have to achieve what that distance is so that you can write the equation. It's important to note that if this distance is positive, If it's greater than 0, then your parabola is opening up, which is what we're used to seeing as a y equal an x squared, or it's going to the right. And if the p is negative, then we are going down or we are going to the left. That's very important, an important differentiation. Now, when you're graphing the parabolas, there's something called the lattice rectum. This is a segment of length 4p, so you have to know what the p is, that passes through the focus and it's perpendicular to the axis of symmetry. This is strictly used for better definition of a parabola. Some of you you'll be given a vertex, you put the vertex down and you just draw the parabola. And you don't necessarily get points that are on there. You need the focus. This gives you better definition so your parabola is more accurate. Okay, now what I'd like you to do, so I hope you got that vocabulary. Now I would like to apply it and you actually see it in motion here. So I'd like you to take the other part of your notes, get this set up, tape this on your paper, and we will go through this chart now, so that you can pause the video if you need to before we go through this. I have separated it into two different directions. So this is up and down, this would be left and right. And it's a very important differentiation when you're doing the graph. Let's look at the vertical one. You're used to seeing a parabola that goes up and down. So this equation right here has the vertex as your origin. And the axis of symmetry is that y-axis. Now the focus is going to be a distance of p, right? So this distance right here is p. And remember, if it's going up, that has a positive p. So this distance right here, we could call that line the lattice rectum. If this distance was 2p and this distance was also twice p. Okay, that would be the lattice rectum. That gives you a better definition. Now, you can also have vertically going down. Or let's talk about the focus for a minute before I do that. All right, so the focus is on this line, 0, and it's a distance of p. So it's either, we're going to go, that's a positive p, we're going to go a negative distance p down here. So you can also have the parabola going down. Okay, this side's a little crooked, but you understand what I'm saying. This would be also the distance of p, okay, but it's going down, so that would be a negative. The directrix would be the line that is the distance p. So if I did the line here, this would be the directrix, which would be a line of y, because it's a horizontal line, equals either plus or minus p. So this is the directrix for this parabola, and this would be the directrix for this parabola. Okay, it's a little confusing to do two graphs on one, but I want you to really take away that if it's x squared equals some number 4 times p times y, that is going up, it is vertical, and your vertex is at the origin. Let's look down here. Let's still do the vertical. So the only difference here, you still have the 4p, that distance to the vertex and the directrix, but now you have an h and a k, which means our vertex has shifted. You see, if h is 0, then I just have x squared. Boom. If k was 0, if I was at the origin, I would just have y. So if you really only memorize this equation, and then if you're at the vertex, h and k are 0, Boom, you've got that equation. So we haven't changed anything other than now we are shifting. For example, if I draw my parabola over here, there's my vertex, okay? I have now shifted such that here I've come over H and I've gone up K. So this vertex is now at H and K. My axis of symmetry is now going to be whatever goes straight through there, and now that's going to be wherever my H is. So this is going to be x equals H. Let's take another one over here. Let's draw a parabola going down. Here's my new vertex. Okay, I came over negative H. I went down negative K. Right? The focus is going to be inside the parabolas. Always, always, always inside. So it's on this line of H. And I'm going to be moving wherever the K is. I'm moving that up or down. So the focus starts at the vertex K, and then it moves up or down depending upon whether my parabola is going up or down by the distance P. That's why real important to have the distance P. Now the directrix here, okay, that would be the directrix. It's the same distance P. Here I would have the directrix. So if you notice, it moves, it's a horizontal line, so you have y, it's not really a point, I don't need a parenthesis, y equals, and it shifts from the K value up or down the distance of P. So this is just K plus or minus the P, is that line. Okay? Now, let's stop and pause for just a moment and remember that if you have a parabola, let me grab the blue one. This parabola, okay, has a positive P value, and this one has a negative P value. This parabola here going up would have a positive P value. This one going down would have a negative P value. So you need to remember up, positive, down, negative. Now that's the vertical. All right, let's look over here if we can do a little bit of the horizontal before we go to the next video. If you're horizontal, which you have not done as much yet, you're accustomed to this. This is easily in the calculator, the vertical, the y equal x squared. But you notice we're putting the x squareds on one side of the equation. This is our standard form now. You go vertically, and this is much more challenging to put into the calculator. So you need to understand this. You're not going to be able to check all of these on the calculator. Now, if you have a y squared, again, you still have the 4p, but now the x is on the side with the 4p, and this is a y squared. So let's go to the right first. You're going to have this parabola. The vertex is at the origin, and your focus is always inside. All right, this distance of P, and this is your focus. The directrix would be this line right here. It would be the same distance P outside the parabola. So that's the directrix for that parabola. Okay? Now if I was going in the opposite direction, if I was going left, then I would have a negative P. This would be my focus, and this distance would be a negative P. All right, let's pick up here when we come back in the second video.